Okay. It's already 6:10, and although no one has joined, let us start today's session. You can always access the session through the YouTube video which what we are recording, and that you'll get through the NPTEL team. So from that point of view, there is no issue. Okay. So let us start today's session. So today's session will be mainly on theoretical aspects of heat treatment processes, different heat treatment processes what have been covered in the earlier video lectures. We'll go through that and we'll brush up the things once again. So mostly it will be all theoretical aspects of heat treatment process. So if we move to the first question, it is on normalizing process. So it says that during normalizing process of steel, the specimen is heated. Sorry, the specimen is heated above the upper critical temperature and cooling in steel air, or below the upper critical temperature and cooling in steel air, or below the lower critical temperature and cooling in steel air, and or above the upper critical temperature and cooling in furnace. So let me try to once again briefly explain what is normalizing process, and then we'll discuss about the we'll discuss about the answer of this question. So if we see normalizing process, it's kind of one of the most widely used heat treatment processes, right? So normalizing processes is mainly applied on almost all castings, overheated forgings, very large forgings, these kind of components. Always this normalizing is always done as a heat treatment process. Now why normalizing is used? Mainly to do some refinement of your grain structure, or you can improve your machinability, or you can relieve the internal stresses whatever is producing during your cold working process, and also sometimes to improve the mechanical properties of the structural carbon and low alloy steel, right? So if you try to note down what the advantages of normalizing process. So let us note down the thing. So the first one is refinement of grain structure. Then what else? You can improve your machinability. Machinability, and then you can relieve the internal stresses whatever is producing. Relieve the internal stresses, and then you can also improve the mechanical properties. No, improve. So you can say these are some salient features of normalizing process. Whenever you do some normalizing process, these kind of advantages you will always get. But how will you get these kind of advantages? So if you see normalizing process, this consists of what? Heating of steel above the upper critical temperature. So heating of steel is happening above the upper critical temperature. So let me draw the thing a little bit. So if you have this, phase diagram. So this axis is composition, right? And this is basically carbon composition. And here you have across the y-axis, this is temperature. Now in still, if you are thinking of this eutectoid still, this is 0.8% carbon, and then let's say this temperature is somewhere around 900 degrees C, and this temperature is, so this is your lower critical temperature, correct? This is your lower critical, and this is your upper critical, right? And here you have this austenite. So this is gamma austenite. Here here you have this ferrite plus austenite, and here you have this austenite plus cementite, right? So the range of normalizing is basically here. So the range of normalizing is basically here. This is the temperature where you should go up to, and then you are cooling in still air. So basically what is happening is like normalizing is consisting of heating of the steel above this upper critical temperature and then holding at this temperature for a short period of time depending on the type of steel, correct? And then you can achieve you can achieve sometime homogenization of this austenite hypoelectric steels, that those are heated to 30 to 40 degree C above this critical temperature, correct? And then you can hold at that temperature for let's say 20 to 40 minutes depending on this chemical composition, and exceeding this uh, exceeding this temperature range might result in excessive austenitic grain growth, right? So what happens is like there can be some excessive amount of grain growth if you are exceeding the temperature for a longer period of time, है ना? Now, now what happens is after this desired holding time has elapsed, the components are cooled in still air. So, what is the resultant microstructure? Is the resultant metallurgical structure is composed of fine perlite with ferrite in hypoelectric steel. So, the microstructure consists of fine perlite with ferrite in hypo, correct? In hypoelectric. Okay. I think up to this much of point, this should be understood, and it will be noticed that that the newly formed grain boundaries do not correspond to old ones basically. So if the initial structure is coarse grained or irregular kind of thing. Normalizing leads to a considerable improvement of this structure together with improvement in mechanical properties, right? So in the same way you are doing this austenizing, homogenization of this austenizing, the normalizing of hyper-eutected steel is done also by heating the steel to 30 to 40 degrees C above this upper critical temperature and holding at this temperature for a short period of time and until the complete phase transformation has takes place and subsequently again cooling in air. So both for hypo and hyper, the process is same, and this operation is done not only to refine the grain size but also to um, like you can dissolve the networks of carbides that may have been developed during this forging or rolling or whatever cold working operation you are working with, and in some instances during case carbonizing also. So that is another heat treatment process where the carbides can be dissolved. And this at room temperature, the newly formed structure consists of fine-grained perlite with cementite for this hyper-eutected steel. Correct. And this normalized structure is like more suitable for spheroidizing treatment to obtain a good machinability. Now, now the mechanical properties obtained after normalizing depend on how you are cooling the material, how fast you are cooling or how slow you are cooling. So all depends on this rate of cooling in air. So a faster rate of cooling may result in higher strength and great hardness, uh, and the vice versa. So if you are cooling at a slow rate, you are compensating the hardness basically, right? So hence when increased strength and hardness are required, the cooling rate may be enhanced by using, you can use some fans, some forced convection kind of thing, right? And yeah, so normalizing is mainly adopted on this plain carbon or low alloy steel. The hardness resulting from this treatment depends on this dimension and composition of the steel and the rate of cooling, as I said. So yeah, now coming to this question, during normalizing process of steel, the specimen is heated. Yes, of course, this is heated above the upper critical temperature. This is heated above the upper critical temperature and cooling in steel air. Right. So option one is correct. Okay. So let's move to the next question. Then question 2 says the process of obtaining spherical grains of Fe3C in steel in the process of annealing is known as what? Mud tempering, spheroidizing, hardening, and none of these have. So from the question, of course, as it is saying the spherical grains, this is common sense that of course in spheroidizing you are getting some spherical grains over the microstructure. So again, let us try to brush up the things of what is spheroidizing or what happens during spheroidizing process during some annealing process. So spheroidized annealing is kind of it is done by heating the steel just above or slightly below this critical temperature for a prolonged time followed by a slow cooling. So again, let us try to draw the phase diagram. So always the figures always helps to understand it better. Now, if this is your phase diagram, this is your composition, so this is carbon percentage, then this is temperature. Now, the same I'm talking for this eutectoid still. This is 0.8%. This is gamma austenite. And then this is ferrite plus austenite. This is cementite plus austenite. And then this is ferrite plus perlite. I hope these things are very much clear from the iron carbon phase diagram. So there should not be any confusion. And then the range is here. The range is So this is your the temperature range where you should the heat where you should heat up your material up to the lower critical temperature. So basically you are hitting the steel just above or slightly below this lower critical temperature for a prolonged time followed by a slow cooling. So during annealing, sorry, take this one. So during annealing, always do slow cooling. So how you are doing slow cooling? Of course, you are using some furnace. So there is no use of external arrangement like happen in air or water or oil bath or anything like that. So here you are doing furnace cooling. That's why this is slow. You leave it up in the furnace and let it cool. Right now, this annealing treatment is adopted to spheroidize the carbides of lamellar pearlite or secondary cementite. So yeah, so this treatment is adopted to spheroidize the carbides of lamellar pearlite or secondary cementine. Correct. So this is also done to transform structures such as the hard and kind of brittle structures like martensite or trusite or sorbite. These kind of structures also can be transformed through this spheroidized annealing. And yeah, with these kind of structures is basically produced by quenching process, right? So you do some oil or water quenching of to get these hard structures like martensite, trusite, and yeah, spheroidized annealing can be used to transform those things to induce some ductility into that. Um, as I said in this figure, this is done. The heating is done up to this slightly below this lower critical temperature, and kept it there for prolonged time. The purpose, what is the purpose of this spheroidized annealing? Is like you want to improve the machinability always, and in some cases to improve the cold formability also. So it improves machinability, improves cold formability. For example, like for machinability of this high carbon tool steel is that it's based when the structure is globular. So for this high carbon tool steel, the machinability is best when the microstructure is globular. Correct. And you can think of any kind of alloy tool steels, including those of the carbide class, and as well as you can think of this what should I say, ball bearing steel also should have some globular structure in suitable condition for the best machining results. And the methods that are adopted to obtain this globular structure are kind of, yeah. So these all depending on this spheroidized annealing process. Okay. um, Yeah, we'll discuss about this martempering and hardening process also in the subsequent slides. So this is the next question. We should match the correct one. Now, here also let us try to understand. We have already discussed regarding this normalizing process. Let us discuss about this annealing process. Yes, of course, a little bit amount of annealing we have discussed through this periodized annealing process. Let us try to understand it again. And then you have this martempering process and nitriding process. What are these things? And then we'll try to match the correct answers. So, as I said earlier, in annealing is basically kind of carried out to improve this machinability and cold formability to restore the ductility. So basically, you are restoring the ductility whenever your material is too hard to use for your to use as in a machinable condition, right? So you are basically reducing or eliminating this structural non-homogeneity to refine this grain size, and you're relieving these internal stresses to produce the structure of the steel subsequent for this subsequent purpose, right? And annealing is not applied to improve the mechanical properties of alloy steel as such. uh, but yes, you are inducing always some kind of toughness during this heating process. Now there are different kinds of annealing process, like full annealing, process annealing. uh, Let me briefly tell the things what are these full annealing and this process annealing. Now, if you see this full annealing process, this if you see this full annealing process, basically, again, the same thing I am repeating. The metal is heated above this upper critical temperature and held there until the temperature of the workpiece is uniform throughout. है ना? So, if you try to again draw the thing in terms of phase diagram, so this is like this here, this. So the range is basically like this. This is your temperature range where you are working for this full annealing, right? So metal is heated above the upper critical temperature and you are holding there until the temperature of the workpiece is uniform throughout, and finally you are cooling the workpiece at a very slow controlled rate, right? So cooling rate is very slow and controlled, correct? And so this happens in a furnace. So you are doing some furnace cooling here. So basically the temperature of the surface and that of the center of the workpiece is approximately the same. Temperature of surface and that of center is approximately same. Now, what are the benefits of annealing process? These also I had discussed. You can relieve the internal stresses, you can increase the softness, you can increase the ductility, you can increase the toughness, you can reduce the hardness and brittleness. And also basically you are somehow ending up with some producing some coarse pearlite structure. So as you are doing some slow cooling over here, you end up with some coarse pearlite structure. So this can be also you can visualize the thing when you are working on this TTT diagram. So anyhow, these things have been already discussed. Coarse pearlite structure. And what happens in process annealing is basically the metal you are hitting it, it's below the lower critical temperature, that is the recrystallization temperature. So for process annealing, heating is done below lower critical temperature, which is your recrystallization temperature. Recrystallization temperature, again we'll discuss what is recrystallization temperature. So generally this is some zero point 0.6 to zero point 0.7 of the melting temperature of the metal. So yeah, and again cooling in furnace. So the main purpose here for the process annealing is to relieve the residual stresses of low carbon steel. Now, now coming to what happens during martempering. So yeah, we, let me rub this out. So you are doing martempering to induce some toughness in your hard structure, है ना? So again, let us draw some figure over here to better understand the thing. So this is your, let's say this is your time. Let's say this is your temperature, and let's say this is your upper critical temperature from this transformation starts from this austenite, and this is your C curve. Oh, sorry. So there are two temperatures. One is MS, automatic start, and one is MF. है ना? Now, what you do during direct quenching? So in direct quenching, you are basically holding at this hardening temperature for required length of time and directly quenched in water or oil to get the hard martensitic structure, right? So you're directly quenching it like this. So the cooling is not very much controlled, and this is so fast that you are ending up with, so you're not crossing this critical cooling rate, and that's why you are ending up with this hard and brittle martensitic structure. So the disadvantage of this method is firstly that there will be high amount of distortion, right, during the cooling. And secondly, you can say that there can be presence of cracks due to very high rate of cooling in the martensitic structure. So to get rid of those things, the cracks and those like high distortion of those structures, uh, basically tempering is done. So the main objective of tempering is to minimize this distortion and to eliminate this crack tendency of this uh, higher cooling rate during hardening process, right? And it should be noted that tempering cannot prevent these volume changes which are inevitable in any kind of hardening treatment. So if you are thinking of this hardening treatment, always there will be some kind of volume changes, volume change. So which is inevitable, you cannot prevent this thing. Okay, so there are people to join. Anyhow, uh yeah, where I was, yeah, the volume change. So yeah, mud tempering cannot prevent this volume change. So this is kind of inevitable in any kind of hardening treatment. However, it can help to reduce this distortion happening during this larger cooling rate. I hope you guys know the time when to join. This is already 6:41 and I'm already in my middle of this session. Anyhow, please try to join at the time from the next week. So yeah, so mud tempering is basically reduce, as I was saying, this can reduce this crack tendency happening because of very fast cooling rate, right? And what happens in this method is like you are not directly quenching it over here like happened during direct quenching. So what you do is the component is heated to the hardening temperature in the usual manner and quenched in a molten salt bath, instead of employing this water or oil, right? And the temperature of mud tempering bath is kept at a little above this martensitic start range. So let's say this is your martensitic start range, है ना? So what you do, you go up to here, you go up to here, a little above the martensitic start range, uh, the during the starting point of steel being treated, and the component is soaked in the bath. So the component is soaked in the bath until the temperature is uniform throughout. So you are keeping it there for some time. So it is soaking the temperature up to this point. Still, it has not crossed this region. It is not crossing this region, and then whenever you are soaking until the temperature is uniform throughout, but the component is not kept long enough for transformation into binetic structure, right? So here you'll get, if you are holding it for so long time, you'll get binetic structure, right? This is soft in nature. So what you are doing, you are not going up to for that long time, but sufficient time so that it does not cross this region, है ना? You are getting my point, I hope. And then the component is then taken out of the bath and then allowed to cool in air. Sorry, then you are cooling it in air. Correct? So this is your mud tempering. So these thing is basically illustrates the difference of temperature distribution on the component during quenching in water or oil and this molten salt bath. So have you used this to understand what the difference is there? Okay. Now there is something called nitriding process. So nitriding process is kind of surface hardening process. So what are the different kinds of surface hardening we have come across in the video lectures? So there is something called saniding process, then there is something called hardening process, and then in hardening process you have this flame hardening, you have this induction hardening, right? Now, what happens in saniding process? In saniding process, it's kind of a thick case of high hardness and wear resistance is produced on this carbon alloy steels, right? And what you are doing is like your specimen or whatever sample you have, you immerse it in a molten salt bath containing NaCN. So again, let me wipe this out. So in saniding process, sorry, I was a little bit late. Um, yeah, a thick case of this high hardness and wear resistance produced in carbon alloy steel. And what you do is like you immerse your specimen in a salt bath containing NaCN, sodium cyanide. So which you heat it up to some temperature range. Let's say the temperature range is some 820 to 860 degrees C. And then this is usually followed by water quenching. Then you do water quenching, है ना? Now this cyanide bath consists of like 20 to 30% of this NaCN, 25 to 50% of. So basically I'm again brushing up all the things what have been covered in the lecture videos. There is nothing new I am talking about, so don't worry. And then 25 to 50% of is sodium carbon Na2CO3. And the time required for this cyaniding depends on this what depth you need to case harden, है ना? So for 0.15 to zero point 0.5 mm of case hardening depth, you require some 30 to 90 minutes of time. So the reaction is like this. So you have 2 NaCN plus O2 is 2 NaCNO here, and then 2 NaCNO plus oxygen is NaCO3 plus CO plus 2N and 2CO plus CO2 plus C. So this atomic carbon diffused into steel, the work can be directly quenched as soon as it is taken out of bath, and then this low temperature tempering is done somewhere around this, you can say 200 degrees C. And the case obtained by saniding is of high wear resistance. So what you obtain is very high wear resistance and like endurance limit compared to carburizing. So the hardness at case varies in this following sequence. You will have nitriding first, then you have cyaniding, and the least one is carburizing. No? So, what are the advantages of this process? It requires less time than carburizing. Then you require less distortion of the workpiece. Then, as I said, that corrosion resistance and wear resistance is very high. And the disadvantage, you can say, the cost is high for this kind of processes like cyaniding, nitriding. The cost is always high, and cyaniding bath is very much toxic, and hence the worker or whoever is doing the heat treatment process, he needs protection. Now, in case of this hardening process, okay, so let us first match the answers, then we'll discuss of this flame hardening and induction hardening process, what happens there. So for normalizing process, as I already discussed, that it refines the grain structure. So it refines grain structure. What is nitriding process is used for? It increases the surface hardness. Then you have martempering and annealing. So martempering is basically improves the hardness of the whole mass, and annealing improves the ductility. Okay, so yeah, now let us discuss a little bit of this hardening process. So what are the different hardening process we have come across? What I can remember is like there is some flame hardening, some induction hardening thing. Now, if you see flame hardening process, the process basically consists of heating the surface of this medium carbon steel by high temperature gas flame. Uh, the temperature is somewhere around 2400 to 3300 degrees C. So, temperature is somewhere around, and immediately cooling in air or water. So, immediate cooling, water or air. So, this I am talking for flame hardening process. Okay. So you got the temperature, and then you do the cooling in air or water, and uh, you can heat. Heat can be basically supplied by oxyacetylene torch also, like happen in gas welding. So in gas welding, of course, you have this oxyacetylene torch, and through mixture of this oxygen and acetylene, uh, which will be covered in different kinds of welding process. So through mixture of this oxygen and acetylene, you produce this oxyacetylene flame. So you have this oxidizing flame, you have neutral flame, reducing flame. So the my point is, you use the oxyacetylene torch there also. So for flame hardening also you can use this oxyacetylene torch. Now the fuel used by this flame may be uh, this C2H2 and O2. You can use natural gas also or kerosene also as a fuel, and the flame rapidly imparts large amount of heat to the surface, you know. And like the heat is supplied so quickly to the surface, and so for a short time the core remains unaffected. That is the trick. So what happens is like heat supplied so quickly that it cannot get time to diffuse into the center, है ना? So quickly to the surface, so quickly to surface, and for so short time, the core remains unaffected. Correct. Now, as soon as your desired temperature is achieved, the water is immediately sprayed, which cools the surface. Correct. By proper control of this heating and cooling operation, the core is not affected by the treatment, and it's like you can think that thickness of this layer is some kind 2 to 4 mm, and its structure is martensite. So it's like you have at the surface you have this martensitic structure, whereas at the center you have this some soft fine pearlite or benetic structure. Correct. So what are the advantages of this flame hardening? So you can think of like there is practically no distortion of the workpiece because of only small section of the workpieces are heated, and like heating rate is high, the work surface remains clean, and this process can easily be automated. This is very simple method to automate the thing, and the process is more efficient for large workpieces as compared to induction heating. So as compared to induction heating, the process is very much efficient. If you are doing some if you are case hardening some large workpieces, right? And in terms of disadvantages, that the thin section may got distorted extensively, and overheating may cause crack. So these are some advantages and disadvantages you can think of. Now, in terms of induction heating, what happens during induction heating? So there is something called flame hardening, where you are heating up through the flame through this oxyacetylene flame. The heat source has basically changed in these hardening methods. So in induction hardening, it's like the process is again the process is of course employed to increase the hardness, wear resistance, and this endurance limit of the surface of the workpiece. Now, like this heat treatment is given to the surface only by supplying excessive heat to the surface, followed by this drastic quenching. So the basic mechanism is all similar for this hardening process. You do heating up the material and then do some drastic quenching. है ना? So what happens is surface is heated to the austenitic range and then quenched immediately to form martensite. The structure of this core remains unchanged. So for all this case hardening process, the core structure remains unchanged because it is not affected by the heat. And the component should contain, uh, for induction hardening specifically, the component should contain some zero point 0.4 to 0.5% carbon or sufficient alloying elements like nickel, chromium, or molybdenum, whatever alloying elements you are using. That should be sufficient, and or the carbon percentage. Now, what happens is like you are placing your workpiece in some helical coils called inductor, right? The coil consists of several turns of water cooled copper tubing. It's like if this is your workpiece, if this is your workpiece, so it's like you are wrapping it with some induction coil over there. So those induction coil consist of this several turns of water cooled copper tubing. So these are all water cooled copper tube. And then what happens, like alternate current is passed through this inductor, and basically you are setting up some alternate magnetic field, right? And because of this alternate magnetic field, you the field basically induces this some ad current over there on the surface layers, and heat is generated. Correct. And then the current and density is not uniform throughout this cross section of the workpiece. Approximately the 90% of heat is generated in the work layer of the thickness. So there is some relation basically. Where should I write? Where should I write? Ah, okay. Let us write it over here. So there is some relation like x equal to rho by mu f. So this is the layer thickness where heat is getting generated. Correct. What is F? F is frequency. Okay, let me. So F is frequency, and then mu is magnetic permeability, and then rho is electrical resistivity of the metal, the metal, and the heating rate is in the range of some transformation temperature of say somewhere around 300 degrees C per second for hypoelectric steel, and subsequently the heating time is very small. Some you can think of some order of 2 to 50 seconds, very little. And this high frequency current is supplied by motor generator and some vacuum tube generator, and when it is required to increase the strength of the core, the work should be normalized before induction hardening, है ना? So means this hardening process is all about this hardening of the surfaces, and it is the time is so small that it does not get much time to get diffused into the core to heat treat the thing. Correct. So what are the advantages is like time required is very small, and hence the process is very quick and productivity is high. And yeah, that's all for this case hardening process. If you have any question, you can ask always. So we'll move to the next question. So I think I have covered most of the process in terms of briefly explaining the things. So I think for the next questions, it should be easier to understand, or to figure out what the answer should be. So next question says normalizing of steel is done to refine the grain structure, remove the strain caused by cold working, remove dislocation caused in internal structure due to hot working, and all of these above. Of course, whenever you do some normalizing process, like you're heating up the material, then you are keeping it there for some time, and then you are cooling it, steel air. So this is your temperature. So for normalizing, as I said, this should be upper critical temperature. Whatever changes are there, this is because of this cooling rate. है ना? Now, why you are doing this normalizing and annealing process? Of course, through higher cooling rate, you can refine the grain structure, which induces this hardness over there, because you have already gone through this Hall patch relationship. So in this Hall patch relation says that if you're having this more refined grain structure, more number of grains, it can induce more barrier to your dislocation movement. That's why your strength increases, right? Dislocation movement barrier increases. It also can remove the strain caused by cold working, of course, and then it can remove the dislocation caused in the internal structure. Yes, that's also true. So the correct option is all of the above. Anyone? Any confusion till now? and move to the next question. So it says that the recrystallization temperature of steel is how much? 400, 600, 800. I think this is somewhere around 800 degrees C. Now, here, what we should do? We should understand what is recrystallization. Again, of course, you know what is recrystallization. So, you have, of course, gone through this recovery, recrystallization, grain growth concept. Now, in terms of mechanical properties, what happens during recrystallization? Let me emphasize on that part. So, this is already mentioned that mechanical properties, example like strength and hardness of a polycrystalline material, are also this governed by this grain size of this material. You know? So if you are if you draw some graph over here for better visualization, so this is your, let's say, average grain dia over here. So this is in mm. This can be in micron also. I don't know. And then you have, let's say, this is your tensile strength. Okay, let's say this is in megapascal. Now, what are those two things? One is reducing, one is increasing. Which one will be the ultimate tensile strength and which one will be the ductility? So, if you are having some small grain structures, and if you are having larger grain structures like this, which one will provide better strength? The finer one, of course. है ना? So with increase in average grain dia, which is this, your strength is getting reduced. And as your strength is getting reduced, always the strength and ductility are like some vice versa in nature. Correct? Now, yeah, as I said, this nature of variation of these two mechanical properties with this average grain size of this strength and ductility. Now, this grain size can be controlled by mechanical working on recrystallization, as I said, and as we have already seen that this effective size of a grain is decided by uh, what volume by surface area ratio. So this governs your what is the effective grain size actually, and I should actually draw another figure, but anyhow, fine. Like if you have seen like okay, let me draw the figure. Otherwise, this is a little bit difficult to understand. So let's say you are doing some forging operation. So initially it was like this, the workpiece, and then this is you're reducing the length, reducing the thickness, whatever you are talking about. So let's say the grains were like this, spherical grains. So the grains will be elongated because of this cold working process. Is it not? है ना? Now let's say you are doing some rolling operation like this, and let's say this is your final dia, DF, and this is your initial dia. So if you're seeing the initial grains, let's say this is like this, and wherever you are pressing the material, it will get elongated like this. Correct? Let's say for machining operation. Let's say for machining operation. So this is your chip. I'm making some a rough sketch actually. This is your tool over here. So how this will elongate? So these are unaffected parent metals, let's say. So there will be some shear over here, shear over here. So these grains will be elongated like this. correct? Now, so what does this figure basically show? This shows how the grains are deformed by various mechanical working process. You can easily see that effective grain size is reduced because of this surface area of each grain increases, है ना? So whenever you are deforming the material, surface area increases, correct? So grain size, the effective grain size is reduced. Effective grain size is getting reduced. But the thing is, volume always remains constant. You have to have maintain this volume constancy. Otherwise, this rule will not follow. The volume is constant. That's why as the surface area is getting increased, the effective grain size is getting reduced. Correct, है ना? Now, it is possible to restore this original grain geometry by heating the material up to some temperature where these new fine grains are formed. So this process is called recrystallization. And this temperature needed to achieve this is known as the recrystallization temperature, as simple as that. Now, if the material is kept for a considerable period of time at this temperature, then these newly formed fine grains grow in size. That is called grain growth. On the other hand, if the material is cooled quickly, the grain size remains small. So it should be noted that in mechanical working process, the grains are deformed, right? Whereas in recrystallization, new grains are formed. And what is more, their size can be controlled. है ना? So normally the recrystallization temperature of a metal is like, as I said, some 60 to 60 is too much. Maybe some 50 to 60% of its melting temperature, and in the absolute scale, of course. But this temperature depends also on the amount of this prior cold working. So what happens? We should figure out in terms of graphs what happens with percentage of cold working also. Now, let's say this is your percent of cold working. So with increase in percentage of cold working, you are doing some, sorry, you are having this strain hardening of the process. So you're increasing dislocation density. So your strength increases. Now, as your strength increases, of course, your hardness also increases. And as I said, if strength and hardness are increasing, ductility is getting reduced. So these things should be in your mind during recrystallization and cold working things. So these are some few rough ideas of what happens during recrystallization. This is a simple question: as percentage of carbon increases in steel, what decreases? Hardness increases, ultimate tensile strength increases, of course corrosion resistance also increases. So percentage of carbon increase, you're sacrificing your ductility in your structure, correct? Is anybody there? Okay, so let's move to the next question. Here we should match the correct answers. I have already talked about lot of things on annealing, normalizing, direct quenching, and tempering also. Yeah, in tempering, I forgot to mention one thing. Like we have talked about this tempering, but there is something called off tempering also. है ना? Okay, let me first find out the what is the correct answer as such. What should be the correct answer? Mhm. What should be the correct answer? So here tempering is basically you are using some toughening over here. So yeah, before tempering is toughening. Then you are doing quenching. Quenching is basically hardening, of course. Then you are doing normalizing. Normalizing is strengthening, of course, for your faster cooling rate, and annealing is softening. I hope so. Basically, softening and inducing some toughness is both all together. It's the concept is same. Anyhow, um, yeah, this is for some understanding purpose. So here in tempering, I discussed about this smart tempering. Now there is another kind of tempering process which is called ostempering. So ostempering may be employed for certain grades of high strain steels which require a remarkable degree of toughness and ductility over there. So components are like subjected to the process. Subjected to the process to induce this toughness and improve the impact strength, है ना? So there will be some uh, great amount of toughness and ductility will be restored over there, compared to this conventional hardening and tempering process. So ostempering basically replaces this conventional quenching and tempering to obtain this improved mechanical properties, correct? And to decrease this cracking and distortion tendency, as I was saying, during direct quenching it happens most often. So it's like ostempering is done by quenching the steel from the austenizing temperature in the molten bath, and the temperature which is kept just above the level of this martensitic transformation, and the holding time in the bath is such that the austenite is like it's fully transformed into banite structure, and then the steel is cooled in air to the room temperature. So the higher the austenizing temperature, the shorter is the soaking time, of course, and the resultant hardness is lower, correct? So where was the figure? What was the figure? I think I have. Okay, anyhow, uh, let me draw it once again. So this is your time, this is your temperature, this is your transformation temperature, and then let's say these are the C curve, and this is your martensitic start transformation, martensitic finish transformation, and then what you do is like you are coming up to this point, then keep it for prolonged amount of time, and then you end up with some fine magnetic structure, and then you leave it up over there to cool it in air. That is you can tell it like this is the algorithm over here to get some ostempered structure cooling in air. This is what the method follows for heat treatment in ostempering. Okay. Now Here it says the machine tool guideways are usually hardened by induction hardening, flame hardening, vacuum hardening, or mud tempering. So if you see the machine tool guideways usually hardened by flame hardening process. Okay, I've already discussed what happens during flame hardening, induction hardening. We'll skip the part vacuum hardening because this has not been covered in the video lectures. Also covered what is happening during mud tempering. Okay, now for this machine tool guideways, this is usually hardened by this flame hardening process. Now, materials after cold working are subjected to following process to relieve stress. Is it what working? Is it tempering? Is it normalizing? Or is it annealing? So you can tell that, yeah, means tempering also in some way, of course, this is relieving the internal stresses, but mostly annealing and normalizing because you are going up to this upper critical temperature of austenitic range and then keeping it there for some prolonged amount of time, and then you are cooling it. So for normalizing, cooling it still air. For annealing, this is furnace cooling. Anyhow, both the processes are used to relieve the internal residual stress. So both annealing and normalizing is used to, okay. Next, what is the purpose of annealing process? Of course, this remove internal stress, increase hardness. Of course, this is talking about this martensitic range. So yeah, for hardening process is mainly used to increase hardness. Of course, this will not decrease the machinability because you are inducing some ductility and toughness over there because you are heating up the material up to this austenitic range. And so yeah, internal stresses are you are removing through annealing process. Which one of the following groups of quenching media in their order of severity of cooling rate? So if you are talking about this severity of cooling rate, what is severity of cooling rate? Hmm? So severity is basically like you can think it of some a ratio of heat transfer coefficient between steel steel and the quenching medium. and thermal conductivity of steel. So this is how you can quantify the severity of a quenching medium. So it becomes very difficult for it becomes different for different quenching medium, है ना? So the ideal medium will be one which will convert to martensite instantly. Correct. So in terms of severity, there is brine solution first. Acha, from slow to rapid cooling. It asks for slow to rapid cooling. So this one is the correct answer. Forced air. This is slow. Then you have oil, and then you have brine solution. This is my last question. So here what it says that from the lists given below, we need to choose the most appropriate set of heat treatment process and the corresponding process characteristics. So here we have tempering, we have ostempering, we have martempering. We know what happens during ostempering, martempering. Uh, we have a detailed discussion during this live session, and you have some characteristics over here. You need to match with this heat treatment process with its characteristics. So the characteristic says the austenite is converted to bainite, austenite is converted to martensite. So what is the transformation? What happening during this ostempering to martempering in terms of microstructural study? है ना? Now, so if you see in tempering, like both hardness and brittleness gets reduced. So in tempering, both hardness and brittleness reduced. Now, what happens during ostempering? So, in ostempering, you are keeping your temperature range here so prolonged time that it crosses this C curve and then going to fine magnetic structure. Correct? For ostempering, austenite is austenite converts to benite structure. And for martempering, this is converting to martensitic structure. Anyhow, you know the difference between martempered structure and just direct quenched structure now. So yeah, of course the structural transformation will be in the martensitic range. That will not change, of course. So yeah, that's it from my side for today. um, you guys go through the video lectures. If you have any confusion, any problem, you can reach out to me. So I think we can finish it off here. We'll meet the next week. Okay. Bye bye.